Good morning again, and welcome to this webinar. Topic of today is simulation aspects of generative design for the automotive industry. My name is Manuel Gaitan. I work as pre-sales for CAE applications for Siemens Industry Software, and I'm going to be your host today. If you want, you can send questions over the chat, and we will answer these questions at the end of the session. I think we are good to go now. Most of the attendees are already there, so we'll start with this presentation. Avian flight is one of the most energy-intensive modes of animal locomotion. It requires several physiological and anatomical adaptations. In this case, we see this adult pelican. Its weight is about 9 kilograms, its total weight, while its skeleton weighs only like about 10% of it, about 1 kilogram. The bird skeleton is highly adapted for flying. It is extremely lightweight, but at the same time, it can withstand the large stresses of taking off, landing, and flying itself. Well, Mother Nature did a lot of adaptations of the skeleton in order to achieve that. One of them is fusing certain areas of bones, like the spinal column, into single ossifications to increase stiffness. And another very interesting optimization or modification Mother Nature did to the ocean system of birds is the bone itself. Most of them are hollow. It's called pneumatized bones. It means bubbles of air are inside the bones, but to increase structural strength, there are trusses and struts crisscrossing inside the bones. Nature had a lot of time to achieve this perfection for birds, but for us engineers, the time is rather shorter. So we need to find out better ways, quicker ways to optimize the designs we are aiming to in shorter times. And this is the topic for today. That's what we are going to be talking about today. And rather than on birds, more towards the automotive industry. So I'm going to go through this agenda for you. First, we will see topics around defining the requirements we are going to have for certain parts. It is very important in order to achieve generative design to have a clear overview of the context in which we are developing the product or parts of the product. In this case, if we are talking about a car, the dynamics of the car is going to be important. And we're going to see a couple of tools that enables generative design itself. Then we will go through a third point, which is also very important about evaluating the performance of parts or of components of a product that have been redesigned or newly adapted. And because generative design, it's very much attached to new methods of manufacturing, typically 3D printing, we will look also into an aspect of 3D printing that has to do with simulation, which is the assessment of the printing process itself for laser beam melting. I'm going to make this arrow visible for you, and we'll continue. So first, one important or a very useful tool for defining or predicting the dynamic behavior of a car is multi-body simulations. It's the first topic I'm going to talk about now. Multi-body simulation, it's about solving the Newton's law of motion, basically. It's the simplified way you can look at this. It is about connecting rigid bodies to each other each of them having 6 degrees of freedom and being free of moving in space. In order to connect them, we required certain constraints or equations. In this case, in order to connect two bodies using a so-called hinge kinematic constraint, we will require typically 3 constraints to impose equality on the position of points A and B, which belongs to the two bodies we want to connect each other using this hinge, and another 2 constraints to restrict the rotation of the about the orthogonal axis to the axis of the hinge, which in this case is going to be the 3rd axis here. In order to define these constraints, so typically Lagrange multipliers are used to represent the reaction forces and moments at the hinge in order to respect the constraints. This is one of the simplified equations that are to be solved. Typically, it's not only accelerations that play a role in motion analysis, but you will need to account also for damping and stiffness in the system. So this is the way you will typically increase or expand your problem definition. In order to solve this problem, a integration scheme is typically applied. There are a large number of schemes out there. Many of them are grouped into explicit and implicit schemes, where implicit schemes are often more stable in robots for certain applications, but explicit schemes are also very widely used, especially for crash or real-time applications. So the goal here is to create a numerical system that allows solving these equations of motion as efficient as possible. And well, it's not only the solving of the equations of motion which is important when you are really applying this technique for real problems, but it's also the ability to set up a problem, to set up your different load cases, and to post-process the results, which plays a big role. For that, you will find out there a number of professional tools that have evolved over the years and allows you to achieve these goals. Today, I'm going to give you a very quick overview of what NX Motion or SimCenter Motion can do. This is the suspension of a car just sitting on a test bench. Typically, you will have access to your full assembly over the CAD data, and you will have the option of creating a motion analysis out of the original CAD data or out of simplified bodies that you will introduce in your design. In this case, we have the 2 suspensions, the front and rear suspension, fully defined here with single so-called motion bodies, which are which are attached directly to your original CAD data in this case, and they are combined each other with so-called joints, which are the kinematic constraints I showed you before. Along with that, you can define, of course, some other elements like damping and stiffnesses between these rigid bodies, and definitely, well, you will have the possibility of adding solutions, loads, and so on. Interesting is also to mention that this kind of motion modeling can be expanded by applying systemic models of specific parts or specific devices in the car. An example here would be this damping system that is not modeled using explicit geometry within your motion or your multi-body analysis, but it is rather done using a system-level model of fit, in which you can have both the spring properties in a so-called 1D or system-based model approach. Also, the pneumatic damping elements, including the two chambers and the valves connecting them, are modeled within the system. And you will have typically the mechanical connections to the suspension and to the frame also included here. So this is very efficient because in this case you can assess important parameters of the damping system without having to explicitly define it using a full geometry of it. This is also connectable to the full model, and using this combined approach, which would look like this in the software. So you will have typically here so-called mechatronics addition here, and certain input and outputs to connect the front and the rear wheels or suspension to the chassis and to the rest of the suspension. And you will also have the possibility of connecting this here through a specific interface to your one-dimensional, your systemic model of the pneumatic suspension, defined in this case using a so-called Amazon model. So once you have this big setup ready, you can start doing very interesting analysis. In this case, towards ride and handling, we are going to simulate the bump crossing of the car. In order to do this, then we are using this test bench. And here you can analyze, for instance, the extension or the bumping crossing by extending the first shaker by 10 centimeters, for instance, at t equal 1 second, and then half a second later you extend the second one, and you see the response of the car. Interesting is that when you have this kind of mechatronic approach, then you can quickly start analyzing or assessing different types of configurations. In this example, by changing the aperture diameter of the shock absorber, you can change the damping behavior of the car, and you can define that way, let's say, a comfort or a sport configuration, depending on how stiff your damping system will be. One of the beauties of motion simulation is that you can see directly an animation of how your system is really reacting. So you can have an assessment of, or you can immediately verify if your system is well assembled. But moreover, the value of the results are actually in the measurements you can have out of this zone. For instance, in this case, for this analysis, this particular analysis, we have on the rear suspension two measurements. One of them showing the forces acting at the connection point to the shock absorber. So in this case, comparing the comfort mode, which has got a maximum force of 624 newtons, for example, and the sport mode, which has got a larger force as expected of 646. You can also see how the settling time of the comfort mode is larger, and the oscillations are also a little larger than when you are configuring a sport mode. So this is the kind of behavior you want to predict, and you want to have control of the variables in order to do optimization, in order to define further actions, like, for example, tune up the aperture of the shock absorber in order to meet certain requirements, like forces or accelerations at the shock absorber itself, or at some other parts of the car. You can also expand this to even to the experience of the driver. You can control these variables to decide if you are violating certain limits, and you can start, of course, defining optimization loops around these measurements. What else you can do is, well, you were talking about ride and handling, which is one of the first disciplines you can observe using motion simulation, but you can also extend this to more complex problems by applying, for instance, flexible bodies. Flexible bodies is a need if you want to achieve certain goals, like, for example, increasing the accuracy of your forces and your velocities, acting on certain parts. Also, if you want to account for higher frequencies for other kind of analysis within the automotive applications, and also if you want to do, for instance, durability analysis, or to perform a more accurate assessment of certain parts, you will need to define them using flexible bodies rather than typical rigid ones. So, as I mentioned before, if within studies for automotive design, you have a large number of disciplines. If you want to go further into more ride and comfort, or if you want to push this towards vibration and noise or hardness analysis, then you will typically have to increase the complexity of your models. You will have to add more degrees of freedom in order to capture larger, phenomena occurring on larger frequency ranges. So, for instance, by assessing durability, or if you want to do some comfort or shimmy analysis, you will have to go a little further. So I'm going to give a little introduction of what is the meaning of defining flexible models. In this case, typically, if you want to introduce an explicit finite element modeling to a multi-body analysis, is going to be too costly, because the number of degrees of freedom in typical FE models is too large. And because you are solving a nonlinear equation of motions, then it's going to take too long. It's going to be too expensive. In that case, you need to apply a so-called model synthesis to reduce the number of degrees of freedom, but to keep the structural behavior of the part within itself. It requires the part to remain linear within its reference system, and it's based on the fact that ideally you can represent the formation of, or the shape of, a flexible body within a linear range by the summation of the mode shapes, all of them scaled by a participation factor. In reality, or in practice, you cannot take all existing modes, because it goes to infinity. So then you apply a Craig-Bampton methodology to reduce the number of modes, in which you can then take into account the so-called constraint modes and the normal modes, and create a reduced mass and stiffness matrix for nonlinear applications like multi-body analysis. How does this look like at the end? Well, in that case, you can, I'll show you using this video, you can then insert or increase the capabilities of certain parts of your card, like, for instance, the bracket here in the middle. And while you measure the reacting forces, then you can also have a distribution of the stresses on the part. And you can use this information for further analysis, like durability assessments, or you can at least, you will at least know that the forces that you are representing here have a larger accuracy due to the fact that you consider also the flexibility of the parts around the connectors itself. So if we use this information towards generative design, then we have a larger context, a more complete context on which we can apply generative design to certain parts or to complete products. The first tool I'm going to show you is the topology optimization that is used to increase the performance of structural parts. But topology or optimization in a structural sense is about to select the best mathematical design subject to a set of constraints. typically involves an objective, like reducing mass, for instance, and some variables, for example, thicknesses or cross-sections, which are subjected to certain constraints, and typically so maximal stresses or certain deformation levels. You will have 3 types of optimization forms in talking about structural optimization. One of them is sizing, in which you have a predefined form and you can change certain parameters like the diameter of these trusses. You can also have the shape-like topology optimization, in which you can change certain features like the holes on this beam. But these features cannot disappear completely. Only the shape can be changed. And then you have finally the topology optimization, which is also a free-form way of optimization, which is used to create new layout concepts out of a predefined area. Well, finally, basically what you do is you set up a problem in which you have, for instance, this cantilever beam, which is fixed on one end, and there's a force applied at the other end. And what you typically have out of topology optimization is a design that is optimized to the path the forces will undergo for the conditions you set up before. Here you see different results depending on the fraction of volume that was going to be kept in this problem. The problem was the objective of the problem was to increase the stiffness of this cantilever beam while reducing the volume to 1% of the original one. 10%, 20%, 30, 40, and 60%, and so on. And depending on the conditions, you will have different shapes out of it. What's the reason of using topology optimization is very obvious. One of them is you can reduce the weight of structures. You wouldn't imagine that it was going to be possible. In this case, there's this stamping tool that weighs 50 tons and presses with a force of 2,500 tons. So that optimization, topology optimization came out with this new design with trusses are used here instead of the original design with simple ribs. It reduces 20% of the force and it saves energy and finally it saves also money. If you want to see other advantages of using this as well, in general, you will get out of it the best trade-off between weight and strength for your structures. The resulting morphing shapes are very well suitable to be manufactured using additive techniques, and in that case you will reduce the cost of cutting, and you can condense assemblies eventually into single parts, and you can also extend functionality of them. You can create channels, for instance, to transmit oil from within the part. You can add some cooling functionality and so on. Basically, the structural optimization problem is a minimization it's a minimization problem in which we want to find out a vector of variables x that will minimize the design objectives expressed here by fx while satisfying certain constraints here expressed by gx. One subset of this optimization will be shown here, and basically the result of this problem is an alternative x, a vector of variables x, which is part of which is a Pareto optimal, which belongs then to a Pareto frontier and which is better than any other possible solutions toward all objectives designed here, predefined. So in this case, we have this two-dimensional plate. It's subdivided into 10,000 quad elements. Each of these elements is going to be considered a design variable. And we're going to minimize the mass of this vector of design variables subjected to a maximum displacement of one of the nodes here in the middle. The maximum displacement has to be 1.4 or 140% more than the original possible. So in general, we use a vector of field design variable elements that will affect directly the thickness of shell elements or the density of solid elements, and also the Jones modulus, which is related to the stiffness of the problem. So the stiffness of the structure. By using an iterative process, we then change the global matrices of stiffnesses and mass until we find an optimum towards the problem described before. Typically, you will see, or you will find out there, solid isotropic material optimization of one of the most common methodologies to do this, in which would penalize, or the stiffness matrix would be penalized by a certain factor. And the objective here is to vary the vector of filling functions between 0 and 1 in an intelligent way. For that, there is a number of methodologies out there. Finally, what you get is a distribution of the material on your original design space, which was displayed that copes with your optimization objectives and with the restrictions you put on the beginning. So here you'll see the distribution of the material that has got a density larger than 90% of the original defined density. So how do we apply this to more professional problems? So going back to the bracket I showed you before in the dynamic simulation, we can take out of that context and the forces acting on this bracket, and using these forces and the boundary conditions, we can start creating topology optimization tasks. In this case, I'm showing you the capability included in an X. This is the designer optimization tool that is embedded into the modeling environment of an X. This one you will typically do the same thing. You will have to define a design space, and you will define, in this case, this block. You will have boundary conditions or like forces and also certain restrictions for clamping and so on. For that, you will typically use normal CAD features to define all these boundary conditions. And also you can define, well, typically so-called manufacturing restraints, like for extrusions, like you have a construction in a certain direction that you have towards the additive manufacturing. You can also define maximum angle, overhang angle towards certain direction and so on. Well, all these things you will define directly there using these CAD features. Using holes or faces, you can also set up forces and so on. And once your simulation is done, then you can have these kind of results. Which are fairly smooth structures that you can use directly back into your further analysis, or you can take and adapt a little bit and send it to the 3D printer for and typically for laser beam melting applications. So this is the result of one single topology optimization run, let's say. So this is one cycle. But what if you want to extend this and to really start looking or taking into account additional design variables, not only the structural ones we had here in this case. Well, in this case, we took the forces coming out of the analysis of the multi-body analysis, and we got this one design. But what if you have to take into account other aspects like the price of the material? Maybe you want to also explore what happens if you change the connection of these bolted points. You can move them perhaps left or right a little bit. What if you have more freedom to start analyzing this tool? Then in that case, you will move into a different level of optimization, which is called design space exploration. And for that, you have the possibility of expanding towards finding global optimal designs, or designs including different aspects. How does this work? Well, design exploration is it works based on parameters. It's not a topology optimization, but it's a parametrical optimization. The best way to explain this is using this example. Here we have a electronic device, and we want to increase, or we want to optimize the cooling behavior of it. For that, we have openings for air. We have a fan here to pull air out of the electronic box, and we have some heat sinks. We have access to the variables controlling this, so we can move these openings along this wall, for example. We can also move this fan along the opposite wall, and we can change the diameter and number of pins or of needles to compound in these heat sinks. So we can set up a problem that starts testing and combining all these design variables in an intelligent way in order to minimize the temperature on the devices attached to these heat sinks, and also in order to make the temperature distribution within the electronic device as even as possible. So we can start then doing this optimization, and while it's running the different possible configurations, the algorithm is looking for those feasible designs that will lead to the objective we are looking for. You see here the development of the mass of the heat sinks, which is the restriction of or one of the objectives. You can see the number of design variables you are using to achieve the minimum mass. So at the end of the day, you say, well, we found out a design that reduces the mass by a certain percent, and we improve the cooling system also at the same time. Of course, we had access to different variables. So this is the improved design or improved setup we found. How does this work? Well, this is like, in general, optimizing or design exploration is like climbing a mountain. You have a design space, which is your terrain. You want to start here underneath and conquer the peak. But you don't know how the way is. It is icy, it is, you have heavy snow, you have loads gravel. How the way is going to be, it's difficult to know for you because it's the first time you climb this mountain. So if you go there on your own and you rely only on a certain type of equipment, it's going to be probably difficult to get up there. What you would need is a Sherpa that knows how the terrain is, that takes you through the correct paths, that helps you carrying out certain parts of your equipment, and someone that knows how to get there as better as possible, and as fast as possible. This Sherpa is a search framework. It's a hybrid algorithm that takes advantage of different optimization strategies. It looks for global optimals, and it takes advantages of the best of each of the optimization methods out there, while it it is doing that, it tunes itself to adapt to the design space and the restrictions you put into the problem. And it's very efficient for different type of problems, even for the complex ones. The idea here is to change a little bit the traditional optimization problem or process, in which typically you will have an original starting point. You define the objectives. You will have to simplify the model in order to make it manageable. You need to select the proper algorithm. You need to tune out this algorithm, do the job of looking out for sensitivities and so on, conduct research, and interpret the results on your own. And this process is difficult. It requires many iterations, a lot of expertise. It's error-prone, and it's the way you would try to climb the mountain without help, let's say. So using a more professional design exploration tool, we put all these steps together. We don't have the need of simplifying the model anymore. The selection of algorithm will be done automatically, or better explained, it will look for all possible algorithms and select the best one depending on the type of problem you have, and it will do the interpretation of results also for you. It will help you with that. Yeah, there's this method has been validated quite a number of times. This is an example using a standard function. You can see the development of the function for n equal 20, and compared to the old algorithms out there, or not all of them, but many of the common algorithms of optimization, and you see that this Sherpa algorithm will go and find the optimum not only quicker but more closer to the known optima. So how it looks like when you combine this with topology optimization. Well, typically, what we want to achieve here is a comparison between different materials. So we want not only to optimize a part towards its structural properties, but also to optimize it towards the material cost and take into account certain safety factors. So the objective here is to find out the lightest lightest design, considered as a safety factor of 2, and we are to analyze about 8 different materials and to find out which of them it's going to be the best one towards those restrictions, but also towards the price of the material itself. So we see here the results of the result story of this different materials. I'm going to jump here into the okay. Here it's going to be yeah, exactly. Oh, sorry. Here you see after the optimization problem has been run, you will have here a table summarizing your study, including all possible design variables for the different materials you selected. So, and it is weighted towards the important restrictions you put into the problem. So you see here the designs using the different materials. You see here the cost, the relative cost of the materials between each other, and you see also an assessment of the restrictions you have to this optimization problem that considers the safety factor of the different designs, the mass of them, and the maximal displacement. So in this case, there are certain materials that simply will not meet the minimum requirements. So these are marked in red as unfeasible designs. In this case, magnesium, xenon, and nylon are not feasible because they don't meet the minimum safety factor of 2. This one, the last one, number 8, is also not feasible because it doesn't meet the minimal displacement, the maximal displacement predefined in the problem. So this here gives you already an idea of what designs are feasible and non-feasible, and they are also to be sorted in ranks. Or let's say all possible Pareto compliant results will be sorted in ranks, and in the absolute optimal will be found out automatically by the system, and it's going to be the forged steel because it's the one showing the better performance toward all constraint and objectives. Okay. So this expands a lot the concept of topology optimizations towards a true or a real generative design application, which should really have a system that will take a lot of that would combine a lot of information and that would efficiently and intelligent leads or take you towards a really optimized and generative design. And in this case, because it works together with topology optimization, will be very well suitable for 3D printing or for some kind of additive manufacturing process. So once you found an optimal design, then you might, in most cases, have to go through a short performance validation loop. I'm going to quickly show you what is possible here. Going back to our original design. In this case, well, it's just simply about testing under the same conditions the new topology optimized design or the generative design of your specific part. So towards this bracket, it is just for you to know that typically applications or engineering applications will be there and will have the possibility of testing whatever your new design will look like. In this case, SimCenter Motion can also include, for instance, optimized parts into a multi-body analysis. This is not the only way or not the only framework you want to check things up, but it typically goes to multidisciplinary functions or the wider range of analysis. So SimCenter offers you also the possibility of analyzing your part toward different different applications like thermal and flow behavior of the part. You can also do composites if you have this. It's quite common to combine topology optimized parts with composite materials because it's also very likely for reducing weight. This is also something you can analyze using SimCenter. And you can definitely take the results out of this dynamic analysis and go further to some durability assessment, for example. There are many other areas in which you can also perform studies. And for instance, in the case of automotive industry, it's very interesting and important to have also the possibility of assessing NVH and acoustic phenomena. All these things are available there with using different solvers in linear and nonlinear areas, and applying also different fatigue, and CFD methodologies. All these are also combinable with test and correlation, so the technology is there. Normally, it's important also to validate your virtual models before you start making additional studies. And test and correlation is a very powerful tool for doing that. Finally, the last topic here is it's about predicting problems during the 3D printing process itself, specifically for laser beam melting technology. With that is meant powder bed 3D printing processes. This is included here in this presentation because all this generative design stuff is tailored to be printed with this technology. But 3D printing is not that easy. It generates a lot of scrap normally if you don't take care, if you are not that experienced with that. You can very likely generate designs that are not printable, let's say, that could cause different number of problems. And the idea is to offer you the specific tools to predict if your part is going to be printable or not, and to reduce the scrap percentage in your printing processes, since these are not, these are costly, definitely. Where this scrap is coming from, well, there's a number of challenges to look at. So the most common one is the thermomechanical history. It is related to the thermal stresses created during the printing process itself. This leads to deformation, and this deformation can be so high that the recoder of the printer can collide with the part, destroying the part, stopping the printing process, or even damaging the machine. Local overheating would lead to bad surfaces, as you can see here on at the edges and tips of this specimen here. Thermal stresses can lead also to the lamination of the part and to shrinking lines when thin walls meet together and create a larger cross section. And while there are also some microstructure defects related to porosity and so on that can also lead to lack of quality in your 3D printed parts. So we want to offer you a tool, a possibility of predicting this phenomena, and I'm going to show you using this small video a little bit how it works. And this is the closing point. So typically you will have your part ready to printing, including all your support structures in the additive manufacturing module of NX. And you have to create an homogenized distribution of these support structures that would be attached to the part you really want to print, and set up some parameters for slicing and printing itself. Homogenization is there to be able to mesh the part and put things together. You see here the definition of all material and printing parameters on your part. These are automatically applied to the supports and to the specimen itself that is going to be printed. Afterwards, you will have to create a macro slicing approach or strategy. It depends on the topology of your structure, how fine this is to be defined, but normally for a mechanical analysis, you have slices that are about 1 to 3 millimeters. In this example, these slices are a little larger for the solver to go a little faster. The meshing and setting up of boundary condition is done automatically, and what you see here is already the results. In this case, the thermal analysis, it shows you over the building or the 3D printing process layer, macro layer by macro layer, how the temperature distributes. maybe you see that on the left part that is not supported, the temperature is way larger than on the other side, for example. So the kind of analysis or information you can get out of that. You will also have right away a assessment of the distortion of the part, which is one of the important things you want to know after such simulation, in order to first to know if your part is going to be usable afterwards in the application you have, because if it's too largely distorted, then it's not going to fit in your full assembly. But also to predict if the part is likely to collide with the printer. In this case, we left on purpose the left-hand side non-supported to see the difference between a supported and a non-supported effect, and to create artificially a collision of the part. So you can, of course, animate the way the part deforms. Before looking into the recorded collision, we look into the local overheating. Local overheating is very important information. It tells you about the quality of the surface, and well, the quality of the surface would also have an impact on the strength of your part and on the durability aspects. This tool predicts which areas of your design are likely to overheat and where you might want to put additional supporting or heat sink structures or change the geometry, either way. Once you have this, another interesting information is, as I mentioned before, the recorded collision detection. You will have here a report of areas where this is likely to happen. It tells you at which layer this happens and by which measure. And very interesting is also the possibility of creating a pre-compensated model depending on the level of deformation or distortion you had before. So it will go multiply your deformed structure by a certain factor, typically -1. And here you will see how the original design looks compared to the compensated one. So the compensated is orange, and you see which areas are the pre-deformation has taken place. So we are approaching the end of our presentation. I just want to summarize what we saw today before we start with the Q&A session. So we went through a definition of requirements. Using multi-body analysis and including flexible bodies, it's possible to have a very wide and very vast assessment of the context of your problem. We had topology optimization and design space exploration as tools for enabling generative design, creating innovative designs and to really go for optimal and take out of technologies like 3D printing the most advantage of. We also had a little insight into product performance validation. Well, it's using multi-body analysis and other tools. You can first define if your part is really going to work for the application it's meant to. And we had also a insight on the 3D printing process itself and how to predict the success of printing of your part using also simulation technology. And with this, I would like to close this presentation and thank you, everyone. If you want to have further information, there is my email and contact data. You can send me an email anytime. I just would like to thank you again for your time and hope to see you next time.
Siemens, ingenuity for life.